Hello! Hello, everybody! Welcome to the LIUniverse. I'm Dr. Charles Liu, your host, and it would be really great, I would personally appreciate it greatly, if you would call me Chuck. Anyway, we have a wonderful show today. I'm really looking forward to it, and as always, we will begin by introducing our co-host, Allen Liu. Hey, Allen!
Hello.
Anything exciting going on today?
I mean, it's just generally nice weather. We're got summer recording going on. It's gonna be good.
Oh.
I might have gotten a drink from a large chain.
Yes, drinks from large chains can sometimes be a joyfully cosmic cool thing. Well, maybe not cosmic, but cool. Yeah, anyway,
Definitely cool.
very, very nice. And I am very, very happy to have with us today as our special guest, Dr. Tom Rice. Tom, hi, thanks for being with us today.
Hey everyone, it's good to be here too.
Thanks, Tom. So, give us a little sense of what kind of science that you do, the things that you've been doing research on over the past, I don't know, a few years. What you got?
Sure, yeah. I mean, I study star and planet formation, so I study how solar systems form, how they come together from the stuff that's out there floating in our galaxy, like gas and dust. And I can, give you a deep dive into a couple of those like specialties that I've got. Basically, the big question is, how did our own solar system get here? How did the Earth form? And how commonly does that happen elsewhere in the universe? And how often does the
Yeah,
conditions necessary for life come about?
That's a
it's
great
exciting.
point. Yeah, because right now, I would say that probably the place where astronomy is making the greatest leaps and bounds is in this concept of exoplanets and planetary formation. We're finding so many of them now. We should really know, right? We hear people saying, oh, there must be billions or trillions of planets out there. Really? Is that actually true, or is that just an extrapolation from a very small sample? So you'll be able to answer that question for us. Is that right?
I'll do what I can to tell you what's known.
We will
That's the
accept
best
that.
we can ask.
So we now share and discuss today's joyfully cool cosmic thing. And it is
Woohoo.
about a discovery that has been made using the James Webb Space Telescope. Now, that's been getting a lot of news lately, of course. Really, one of the most magnificent astronomical instruments ever built. And it's out there and taking amazing pictures for us to think about. This particular data that the James Webb Space Telescope has been gathering is spectroscopic data about a brown dwarf. There's a brown dwarf called TWA 27b, and a recent paper suggests that this brown dwarf is a baby. Uh, what do we mean by baby? A, young, right? B, small. But what's cool about it is not only is it young, but it's growing. It appears to
Hmm.
be adding material on it. We are literally watching a baby brown dwarf grow into an adult. I think that's an amazing thing. I think that's remarkable. Tom, give us your sense of this amazing discovery.
Sure. I don't have a lot of details in front of me, but I think there are some things that are really interesting about the study of brown dwarfs. So this is, I don't know if your viewers are super plugged into the discourse about
Ah, go
what a
for it.
brown dwarf is, right?
Yeah, yeah.
So
Fill us
yeah. So one of the things that astronomers learned over the 20th century is that stars are these balls of gas that are burning in a nuclear reaction, hydrogen or other elements in their cores, and that they do so for a very long time. And it's easy for a really big ball of gas to burn hydrogen, and it's very, very hard for a really small, relatively speaking, ball of gas to burn hydrogen. And eventually you get to a point where you get smaller and smaller and smaller, less and less mass, that there is a certain size of ball of gas that's just not massive enough to ignite hydrogen fusion in its core for a sustained amount of period. And so we in those objects that fail to burn hydrogen in their cores, they don't get bright and stay bright. In fact, they just kind of cool off and turn kind of brown, and they become very dim. And so the term that we've come up with for those objects is brown dwarf.
cool.
And so that's a bit of star formation and kind of stellar evolutionary theory for you. The fun thing about brown dwarfs and what makes them, I think, particularly interesting to study is that because they're not doing the whole nuclear fusion thing, they're
Yeah.
not they're too small to be stars. They're also bigger than any planets we know about, and so they
Oh,
kind of occupy this intermediate zone. in between a star and a planet. And when I say planet, I'm mostly referring to like a gas giant like Jupiter or
Oh,
something like
Yeah,
that.
so
So
we're
brown
looking
dwarfs.
at
so brown dwarf is like diameter wise in size significantly larger than Jupiter, but say smaller than the sun.
Many brown dwarfs will be about Jupiter sized, depending on how their cooling
oh,
processes have gone. There's a whole
they're just a
complicated
lot
story.
denser, right?
Yeah, so I mean, we would have to go into like a graduate level course in astrophysics to talk about the diameters of these objects and why they are the way they are. So
Yeah, yeah.
when
I
I
looked at
say
them.
bigger or
That
smaller, I'm
sounds
mostly referring
crazy.
to mass, if that's okay with
Yeah,
you.
that's
Okay,
totally
okay.
fine.
Yeah.
So if I remember, these are things like 50 times the mass of Jupiter-ish.
Yeah, I think 50 to 80 was a reasonable. Excuse me, let me back up. The low. Usually, we talk about objects entering the brown dwarf regime from the planetary regime at around 13 Jupiter masses.
Oh,
So
Okay.
you can actually shove, 10 Jupiter masses worth of material together, and you'd still consider it a planet in this scheme. But once
oh,
you go over
Okay.
13, now you're in a regime where you're thinking about them as brown dwarfs.
Nice.
oh. So
Yeah.
13 on up, but
Yes.
less than about 80. Okay.
And
So
then for like, I was just thinking also for the temporal scale, we're talking about these being baby objects. That still means they're like a million years old or something.
Different people have different standards for what they mean when they say young in this context. But
ah,
Okay.
if you're watching an object that is still accreting mass, so it's still pulling stuff in from a disk that's around it that it was born with,
Yeah.
that object is going to be in the 1 to 10 million year range,
hmm.
Awesome.
Okay.
ballpark.
Well, that's great. 1 to 10 million years definitely counts as young when we're talking about the age of the Earth, for example, or the age of the sun being more than 4 billion years old. Right?
Oh, yeah.
Definitely fair.
Yeah, it's exciting. So, does your research involve thinking about planets that are only a few million years old, Tom?
That's a good question, right? So I'm actually actively working on a project this summer that actually references some of Kevin Luhman's other work.
Oh,
Nice.
Kevin Lubin
Focusing
being the scientist that made these observations with James Webb.
exactly, yeah. So the person who's been referenced that we've already been talking about, a lot of the work that I have actively going is studying the youngest brown dwarfs that are at that age of 1 to 10 million years. And they're probably still accreting some matter, and still settling into what their vibe is going to be like as they migrate through the cosmos, and how they're going to settle into how we see them later. So
Exciting.
yeah,
Very exciting. Now, do you like the term failed star for brown
yeah.
dwarfs? I mean,
Ooh.
you hear that so often in the sort of general conversation about brown dwarfs, and yet I feel like they're not failures. They're just what they are, right? I mean, I don't know. What do
I
you
think
think?
that's a really funny question. Yeah. I mean, I think it's useful pedagogically. I think if you're learning about how stars work, it's useful to have this framework of, okay, a star can achieve this fusion burning, or this object can fail to do that. And so,
Mhm.
from that point of view, in setting up what they're doing and kind of what the categorization scheme is, I think it's a useful phrase. But as a fan of astronomy and as an appreciator of the natural world, I think we can do something like that.
Yeah.
Yeah, I think we talked about this with one of our previous episodes. Someone was saying they're overachieving planets, maybe.
Ah.
Yes.
I mean, we'll vote for overachieving planet around here. Okay.
Yeah.
Although there are a lot of syllables in overachieving planet. That's okay.
Eh, it's fine.
We'll move on. Okay, well, I think this is a good time for us to ask a question. Tom is
Cool.
here and able to answer questions about planets and solar systems and stuff. Alan, do we have a question from a student on this topic?
Sure. So this question is from Aliana, who is asking, can a star turn into a planet?
Ooh,
Ooh,
that's a good question. So we were just talking about. I was using a kind of a way of framing the distinction between stars, brown dwarfs in the middle, and planets.
right.
And the main criterion in that conversation that I was using to distinguish between those categories is one based on mass and how mass affects whether something's burning nuclear fusion inside its core or not. But I think
Sure.
there's another split that I'd like to introduce, which is one based on like how something formed. So what's its formation history? How did
Oh.
it get there?
Uh-huh.
Right. And so especially in this framing, the how you get a star is you have this like region of some cloud of gas and dust in some part of a galaxy that gets dense it starts collapsing under its own weight, and then there's going to be some central object in that region that pulls in mass from its surroundings. It's going to suck in mass through gravity, and usually it'll pull in mass from a disk of matter that's going to form around it, something we often call a circumstellar disk.
Okay.
And you're going to get something in the middle that will grow into a star, or if it happens to have too low of a mass, we'll typically call it a brown dwarf if it's too low for it to have sustained nuclear burning. And a planet fundamentally forms in a different process. The planet is something that doesn't form at the center, but that forms in that circumstellar disk of stuff, something that we often call a protoplanetary disk for reasons that are a bit of foreshadowing. Right? And so planets form as a byproduct of star formation. They form at the same time. So like the sun and its planets basically were born at the same time. So because of the nature of that relationship, it wouldn't really make logical sense to form a star that then becomes a planet. Because to form a planet, you need to be around a host star. That's our understanding of it. And so like the timeline wouldn't work. So the answer to the question as written is probably no. If you'd permit me to go on a really fanciful detour outside of what we
love fanciful detours. We love fanciful detours.
So there are some goofy situations in astrophysics where you could take an object like a star and strip away a bunch of its mass through some kind of encounter with another object or something like that, maybe in like a binary system. And in that kind of scenario, you might be able to reduce the mass of something that we usually call a star down to the mass of something that we usually call a planet. And so like that's almost feasible, but I wouldn't count on it happening very often in the universe.
That's fair.
So that's a special scenario. So
exactly.
as you know, I study colliding galaxies, and when the galaxies collide, you have billions of stars converging upon billions of other stars. The individual stars never really hit each other physically, but they pass close enough by each other that they could strip away large amounts of material, right?
Yeah. So that's the scenario that I think is worth considering, or maybe a long-term binary system where there's some funky stellar evolution that happens between the two of them. You get some mass transfer. Another comparable scenario is how some supernova occur. Is you get like a star that dumps a bunch of mass onto a different star and then it explodes. So transfers do happen in astrophysics. I just don't think they would happen to produce something that looks like a planet at the end of it that used to be a star.
That's fair. Yeah, you got like a white dwarf or something.
Very exciting. Right. So that's a great answer to this very interesting question. What it means is that we have to think about how planets like our Earth form in a completely different way from, say, how a star or a brown dwarf would form, right? And as a result, the things that we see on planets should be significantly different from what we see on stars. Isn't that right?
I think so. Can you repeat the specific observable again that you would see differently on planets versus stars?
Well, I would just imagine, for example, their atmospheres, right? What kinds of elements you would expect seeing inside the atmosphere of a planet compared to, say, the atmosphere of a star or a brown dwarf. So there's got to be a significantly different makeup, a composition thereof, right?
Yeah. So this is, I think, a really valuable conversation because there's different kinds of planets. And if we look at our own solar system, we know that we're standing on a ball of rock that has a little bit of water and a little bit of air around it. Not all the planets in the solar system are like that. We have a bunch of very large planets that are mostly from the outside to the inside, mostly made of gas. So when you're comparing the atmospheres of stars to the atmospheres of planets in terms of, and I think you were just focused on composition just now. The composition of the planet Jupiter is very, very close to the composition of the sun.
Interesting.
And that's, they formed out of very similar material, right?
Yeah.
A planet big enough to be as massive as Jupiter, the only source of mass that can give you enough stuff to build a planet as big as Jupiter, the only reservoir, the only source of all of that stuff is going to be the hydrogen and helium floating around in the kind of the birth cloud of a star like the sun. And
Okay.
so the sun sucked up a bunch of that hydrogen and helium and trace elements. Jupiter also sucked up a bunch of hydrogen, helium, and trace elements. And
Uh-huh.
so their compositions are going to be quite similar. The main difference that you're going to see is that Jupiter is much, much cooler. And so there's going to be
Mhm.
molecules that form in its atmosphere that would remain in the
Makes sense.
atomic state in the sun. I'm getting very
Okay.
technical here, but I think you asked this question.
Hey,
So
atoms and molecules. I'm cool with that. No, that's great.
Mhm.
Yeah.
Yeah.
Yeah. So, but Earth has mostly like nitrogen and oxygen in its atmosphere, right? It's
And it's a
nothing
much
like
smaller
the
atmosphere
hydrogen
too.
helium. Right. And it's much smaller and it's warmer than Jupiter because it's closer to the sun. How does that gather? How does that kind of material like literally support life as we know it today?
Ooh, good question. Right.
Yeah.
So I mean, I'm not a biologist, although I do study astrobiology, which is just the
Ooh,
study of life in the universe.
cool.
And
Okay.
so I can talk about this in very broad terms, but when we
Yeah,
start
yeah.
asking questions like what exactly does life need, I'm going to say, oh, it needs some carbon and it needs some nitrogen and it needs some hydrogen and it needs some oxygen and some other things, phosphorus,
Mhm.
sulfur. And
The
I'm not
squash,
the guy
right?
to talk to if you want to figure out how to combine those into actual life.
Wow.
But
Makes sense.
I deal with just the bulk elements.
Mhm.
Okay.
So yeah, life as we know it needs a few different things. I think there are folks who talk about the question of like planetary habitability. That's a phrase that
Mhm.
people will throw around.
Right. Hmm.
Or like the Goldilocks zone of like
Yes.
Yeah, yeah.
Yeah, we
you
hear
want to
about
be
that
on
a
a
lot.
planetary surface that's not too hot, it's not too cold, but it's just right for
Hey.
usually what people are talking about is like liquid water. So you want there to be liquid surface water on the surface of a planet in order for it to support life
Right.
as we know.
When we're talking about Goldilocks, what we're really saying is we want the Goldilocks to be just right for our atmosphere because we have life as we understand it based on
Mhm.
things like carbon and RNA and DNA and proteins and things like that, right?
Yeah.
Is that a common thing? Does that happen in planets all around us? I know that, for example, at least the Kepler mission and the TESS mission, these two planet finding space missions, were tuned especially to try to find planets that were like Earth, right? But did they also look for things that were in a habitable zone, whether or not they were like Earth? Things like that?
That's a good question, right? So I am not an expert in exoplanet detection, but I
Oh,
can
you
speak.
have to stop being so modest, Tom. You're not an
I
expert in
mean,
this, you're not an expert.
I'm
You're an
literally not.
expert in all kinds of stuff. No, please, 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 don't be so modest. Just tell us what you
I
know. It's already
I
way more
have
than what any of us
expertise
know.
that helps me understand what's going on. How about that?
That's
Okay.
very humble
Fair.
of you. You're very sweet. Anyway, please go on. Go on. Go on.
So, in the search for habitable, which is to say, like Goldilocks zone terrestrial worlds around other planets or
Hmm.
around other stars,
Mhm.
there are a few different things that you want to look for to really have a successful search, right?
Okay.
So, your audience may or may not be super familiar with like what we call the transit method. So, watching lots of stars, each of which may have a planetary system, and hoping that some of the planets around some of these stars have orbits that are aligned such that the star and the planet will line up every now and then. So
Hmm.
you can
Hmm.
Yeah.
see a little dip in brightness as the planet blocks some of the light. So that's going
Right.
to happen once per orbit if the orbits are aligned just right.
Yeah.
And in addition to needing the alignment to be right, there are also a few other factors that play into what kind of uh, signal you get, what kind of dip that you see as
Hmm.
the planet crosses in front of the brightness of the star. Um, one parameter is going to be what's the relative size of the planet to the star. So if the
Yeah.
star is really small and the planet's really big, then you'll see a big dip in light because the planet will absorb lots of the light. If you have the
Hmm.
Makes
opposite,
sense.
really big star and a really small planet, you're going to see a tiny dip. So it's the
Right.
ratio, it's the relative size of the planet to the star. The planet is pretty much always going to be smaller than the star, but the
Hmm.
Yeah.
relative size is going to show up in the data that you get. You're going to see brightness coming along, and then time's going to go on, and you're going to catch this dip. And how deep that dip is in the brightness of the star over time is going to tell you something about the size of the planet relative to the size of the star. Another piece of the signal that's really important is how often you see those dips. So if it's a
Hmm.
stable orbit and everything is aligned right, then you're going to see the dip every time you have that planet cross in front of the face of its star. And so you're going to be able to pull out how often that happens. That might be once every 365 days if it's exactly like our solar system,
Yeah,
or it can
yeah.
be like once every 5 days if it's really whizzing around there. And
Yes.
we see examples of both of those extremes
Wow.
in the data that we have, right? And so if you're hunting for planets that might have some resemblance, especially in temperature, to our Earth, then you're going to want to focus, you're going to want to look for planets that are not too close to their star, that they're zipping around all the time. Because one of the things we know about how gravity works is the closer you are to an orbiting body, the
Yeah.
faster you have to move to stay in orbit. And
Why
so, really,
Mercury whips around so fast compared to all the other planets.
exactly, yeah, Mercury
Mhm.
is much faster on an orbit than Earth is.
Mm.
And
Yeah.
so when you find planets that are on really zippy orbits, that is usually an indication that they're very, very hot on their surface, probably too hot to support life
Oh, okay.
Makes sense.
All right.
as we
So,
know it, right?
wow, very exciting. And so, you know where I'm going with this. Well, maybe you can guess where I'm going with this. I'm trying to get out of you, like, how many planets out there do you think are actually habitable by our standards, by human standards?
Ooh,
Right.
yeah,
Because once you get that, then we can start talking about the reality of certain, shall we say, classic video games. Things that
great,
we talk about other civilizations and other people and things like that.
Fair.
Yeah.
absolutely, yeah. My understanding of the statistics on how many planets there are and of what kind, um, which would really, a lot of the statistical work came out only in the past decade or so, as
Yeah.
like the Kepler mission was really able to collect tons of information about
Yeah.
lots of different star systems.
Yeah, because it just
Uh,
stared at the one spot of sky for like years, right?
right, right, and they would have gone longer if they could have. The punchline is that most stars, as far as we can tell, based on the statistics that we can do, most stars have planets, probably more than one planet. And the solar systems, the stellar systems that we see in the data that we have are very diverse. And so they have a large scattered range of distributions of distances, different distributions of masses. So there's different mixtures of like big planets close under their star, or little planets, arranged in lots of different ways. And I think that's a really fascinating result. We
Mhm.
live in a galaxy, and almost certainly a universe full of many different and diverse planetary systems.
Wow.
And one of the things that I take away from that is I think it's very likely that there are many, many places in our galaxy and probably in our universe where the many of the conditions necessary for life as we know it would be present.
Ooh.
Hmm. That's exciting.
Now you got to tell us a little bit about the work that you do, and in addition to your research and how that relates to science education or entertainment, astronomy, that kind of thing. Give us a few minutes on that, eh?
Sure, that sounds great. Yeah, so I got this cool job with the biggest professional organization of astronomers, as far as I know, certainly in North America, maybe in the world.
Yeah.
It's called the American Astronomical Society, and so I'm a staff
Yes,
member there.
I am a member. I am a full member, and you are a staff member. So I bow to
Yeah,
you. Thank
sure,
you.
sure.
Thank you for
It's really
everything
supposed
that
to
you
go
do.
the other way, but sure. I'm the one who gets paid, right? And I view my role as figuring out how to organize the professional society towards the end of improving how astronomy education at all levels gets done by the members of the professional society. And
Wonderful.
so I think there are a lot of people in the world of astronomy, professional astronomers or educators or people at universities or people in other roles, a lot of people who are very passionate about making the knowledge and the ways of thinking that astronomers do very accessible and done in a high quality way and done to really empower people's lives. There's a lot of
That's
people who
great.
are very passionate about that cause. And so I really view my role as figuring out how to channel that energy into a kind of collective, coherent way so that people can make a bigger impact.
Oh, I
Um,
love that.
and I'm still learning how to do it, right? I got this job less than a year ago, and
Oh,
there wasn't anybody working in this role before me.
wow.
And so I'm doing a lot of figuring out. It's a real career pivot for me, but I think I'm getting kind of good at it. I
Yay!
really,
Awesome.
yeah.
It's an important job.
Yeah, it's so important, and I'm sure that all of us audience members out there, if you have some suggestions about what the American Astronomical Society ought to do as far as educating or helping members educate and entertain, and otherwise just spread, share our human understanding of the universe,
Yeah.
you got to tell Tom, right? So how do we contact you, Tom? How can we find you? Are you on social media somewhere? Can we follow the things that you
I
have?
occasionally check my Twitter at I call myself Tomer Stargazer. That's TOMR_Stargazer.
Okay,
And you can just email me.
okay,
tom.rice@aas.org would be fine.
yeah. I'm sure that there would be a lot of people be interested in talking about that kind of thing, including, for example, how we could get some video games in there. Super Planet Smasher was that? Uh,
I think Crasher, but I don't.
Super Planet Crasher. Okay.
I think.
I know
Now,
there's Space Engine too is a similar
Space
idea,
Engine. Okay.
or Universe Sandbox, one of those two.
Anything built by Nintendo? Is there like Tears of the Planet Crashers or anything like that?
That
That's a good question,
would
right?
be
So
amazing.
that the Zelda game Tears of the Kingdom has a ton of physics stuff in it, which I'm
Really?
really enamored with. I mean,
Oh,
you can build
good.
machines that follow physical rules
Yeah.
and
Excellent.
fly around in them or use them to fight monsters.
Oh,
So that's
wow.
really sweet.
So does Nintendo like hire astronomers and physicists and science majors and stuff to help
I
them
haven't
build their
seen those
games?
job ads yet, so I don't know.
Maybe they're all consultants. Hmm.
Sure.
Maybe. Yeah.
Yeah. So these are the things that we can all do, right? And especially if we have the AAS dot or AAS.org behind us, right, Tom? And you're there.
Sure.
Our time is flying by. I don't know how much time we have left, but I definitely want to make the point and give you a chance to say something about this. Um, you are fluent in American Sign Language,
That's great.
right?
Yeah.
This is
Yeah.
like so amazing. I think you might be the only one. And for those of you who have been following our TikToks or other like Instagram and things like that, you may remember that when Tom was on there at the American Astronomical Society meeting in Pasadena in the summer of 22, Tom was featured and he indeed showed us his fluency with American Sign, which I think is fantastic. I mean, that must also be another avenue to extend astronomy and the cosmic thing to lots of people who otherwise might not get a chance to do that, right, Tom?
Sure, sure. Yeah. So I come from a deaf family.
Uh-huh.
My folks and some of my aunts and uncles are deaf. And so that's
Oh,
an important part of my, I mean, like American Sign Language and a signing identity is a really important part of what I would call my heritage.
wow.
Cool.
Um, much stronger than other kinds of cultural influences that might have reached me is like I come from a signing family. And so that's really
Wow.
big. In fact, like I moved to Washington D.C. About a year ago, and actually one
Mhm.
of the things that I'm happiest about while being here is that I'm very close to the country's only entirely like signing university for deaf folks, Gallaudet
Wow.
University here in DC. And so I run into like deaf and signing people all the time. I've got a huge community of like friends and acquaintances who are. So I call myself a coda. I'm a child of deaf adults, and
Oh,
that's a term you'll hear pretty often. And so I've got like a big community of codas and of other deaf folks here in DC. And I'm really happy about that.
uh-huh.
So this is, in a
Nice.
certain sense, these are my people. Um, I am trying to figure out how to make sure that I am giving back to my community.
Hmm.
And so the way I'll put this is we live in a country and in a world that is not often friendly or accessible to deaf folks.
Oh,
And a lot of that's really unfortunate. There's a lot of discrimination that deaf folks encounter, and there's a lot of inequality, and there's a lot of lack of access to educational and employment opportunities that are totally
ooh,
needless. Right?
Yeah.
oh,
We could
yeah,
design a better system, and we could organize our society to really
Definitely.
eliminate a lot of these challenges, and we haven't. Which is a really tough and kind of personal thing. And so a thing that I'm very passionate about is making sure that I do what I can to improve access to scientific knowledge, scientific thinking,
mhm,
engagement with STEM issues
mhm.
in whatever parts of the deaf community that I can access. And
Wow.
so part of that's doing some stuff here in DC. I'm working
Uh-huh.
with an astronomy club of students at Gallaudet University.
Oh,
Oh,
great.
Uh,
wow.
yeah. And they've got a good faculty advisor, and they've got a cool telescope. For those on
Nice.
video, Gallaudet is signed like this, so it's two fingers and Gallaudet. So I feel
Wow.
awkward saying it out loud without actually signing its true name.
That's
Um,
marvelous. And it's
cool,
so
yeah.
known that it's just a single sign, a
Well,
single,
yeah,
yeah.
yeah, yeah.
That's
Gallaudet
Yeah.
it's that
University, right?
famous. It's marvelous.
Um, yeah, and for
Nice.
those of you who are listening, I made the sign starts near your eyes, and then you move your pointer and index finger back towards your ear. You'll have to look it up. There's I'm also preparing to participate in some outreach and astronomy education events for the upcoming solar eclipse happening in April of next year. So
Yes.
Yeah. April
yeah,
24th.
yeah,
April 8th,
April
2024.
8th, 2024.
Right.
Yeah,
exactly,
right.
exactly. So
It'll be great.
yeah, so Rochester, New York is home to the only other major educational institution that's
Yeah,
has a huge
NTID. Yeah.
population. Yeah, the National Technical Institute for the Deaf. My dad has an
Awesome.
associate degree from there, so that's kind of
Wow.
Amazing.
part of my my own. I've got like so much oral history or family history there, and so I'm planning to organize with a few other good folks deaf and signing friendly solar eclipse activities.
That's great.
Wow.
Will happen on the campus probably of
Yeah,
our
because it's right in
students.
the path.
Yeah, it's in totality, right? So that's where I'll be next April. If everything's
Marvelous.
planned. Yeah,
Oh, that is so cool. That is
That's gonna be
so
great.
cool. Wow. Okay. Just for that alone, I would go to Rochester for the
yeah,
total solar
yeah.
eclipse. But
We
there may
might
be
meet
other
up
reasons too.
separately because yeah,
Yeah.
it's a local optimum on the weather according to some climatologists here.
Excellent. Oh,
Not
wow.
necessarily a global optimum, but a local one.
I think that's fantastic. Wow,
Yeah.
Tom, that is so cool. I wish we did have more time, but we're going to wrap this up this time and then ask you, can we talk again sometime soon? Like
Sure.
maybe certainly before or right around the eclipse time. You can tell us all about that. We can get deeper into this. We've just scratched the surface, and there's so much more to talk about. There's so much more about the science that I care about. Um, thank you, Tom, for being with us today. Can we find a time to get you back again sometime?
That sounds great.
Okay, it'll be a real pleasure. Thank you very, very much, Tom. Again, Tom R underscore Stargazer on
Yeah,
Twitter,
Summer
right?
Stargazer.
Okay, or email
Nice.
to tom.rice@aas.org. Tom,
Yeah.
thank you so much for being with us today. It was a real pleasure. We learned a lot, and it was a lot of fun. Thanks.
Thank you both.
Alan, as always, thank you so much. I really, really appreciate everything that you do for this show.
Yeah, I'm glad to be here. It's
Yeah.
always a good time.
And for all of you out there, thank you for being with us today. Thank you for being a part of the LIUniverse. And if you like what you hear and see, please consider supporting us on Patreon. And you can always find us on social media everywhere at the LIUniverse. Thank you again. Thank you for being a part of the LIUniverse.